And okay, good. Yeah. All right. So Hans is, as you see, at the SPC in Paris and at Fortaleza in Brazil. Before that, ETH. And then it was Stuttgart, and it was further back to SPCI, and well, back to Saclay after that again. And that's where we met almost 40 years ago. So we know each other, we have many papers together. But Hans is really one of the most cited in physics. He has an H index of more than 100, quite about 100. And well, one of the kings of physics, so please.
Thank you very much, Alex. I'm very happy to be back here in Kolab. I've been here in the beginning of Kolab 2 years ago, so I remember.
Yeah, no more than that.
It was very exciting to see how this blossomed from there. So today I'm going to talk about a very mechanical, mathematical problem that anybody from school with school physics can understand, actually. So I'm talking about the bearings. But first I would like to, okay, so let me first introduce my collaborators. This is Suarez, that everybody knows because he's part of our project, yes. And then this is another professor in Fortaleza, André. Nuno was my postdoc in top professor in Lisbon. Reander is a PhD student in Fortaleza, and Dominique is a PhD student from ETH, who is now in industry. So, of course, there are more people involved because actually I will talk about work that I did over 30 years, and it is many different papers and many different things put together. But these are the principal investigators in this issue of the frustrated bearings. So I would like to first say what is a bearing and make clear that there's a huge difference between 2 dimensions and 3 dimensions, which is actually the main point of the whole talk, 3 dimensions. And then I will talk about what means the frustrating bearings and the properties of frustrated bearings. And then I will have some 2 small extra chapters, one on synchronization and one on space-filling bearings. So a bearing is some mechanical structure that is devised to reduce friction, and it does it by transforming, let's say, sliding friction into rolling friction. So it makes geometry such that you only have no slip. You have between bearings, they can be either discs or maybe spheres. And the important thing is that at the contact, there is no slip, so there is no friction in that sense, yes? But of course, this is the ideal bearing state, but otherwise, before you reach the bearing stage, of course, you will have friction. So there are examples, of course, in mechanics, and I would like to see more of these kind of examples. So you have a bearing which is arbitrarily big, and you see not just these kind of simple one-dimensional structures. So you can think of generalized structures of bearings. And I would like to mention, but not go into the depths, that this kind of bearing stuff, anyway, has many chairs. So here's one chair for you. You can also share it. So there is also a continuum limit of all this story. And this continuum limit is called the Coursera media. The Coursera media are continuum theories which locally on a very small scale you reduce these things to 0 point, like then you have this torque everywhere in the side system. And so the idea of these bearings is to transfer torque from one object to the next. Good. So the bearings appear in many places, but also appear naturally. And many years ago, 20 years ago, with Jan Astrom, we discovered that bearings occur spontaneously in shear bands if your particles are round. So because many people do experiments with spheres in granular media, and when you do that, you find that spontaneously in the shear band, shear bands occur when you shear, when you compress through actually granular materials. And then you see here, the gray particles are those that do not rotate. The black ones rotate clockwise and the white ones counterclockwise. And you see that there inside the shear bands appear regions of these white and black, which you can of course zoom in. And you see that you have these structures of black connecting white and white connecting black. That means you have this kind of bearing, because the bearing you have to always have that there's no slip, so that only counterclockwise particles can connect with clockwise turning particles. And what happens with these bearings in shear band is that they form spontaneously. And when you keep shearing, then they decompose, they destroy it again, it appear again somewhere else. So this is like an immediate state, but it reduces the friction. This is the point. It has, of course, in order to work, to apply some work, because you have to expand a little bit the system in order for these structures to work. So there's always this competition of expanding a little bit, applying some work, and then having frictionless behavior. And these things are also being checked experimentally. A few years later, with Berenger, he did these two-dimensional experiments in which he could visualize rotations by putting on his disk some kind of black line. And then with a camera, you could calculate, measure, all the rotations. And here I saw you the comparison list. Oh, this doesn't work. Yeah. So this is the distribution of spin, of angular velocity of the particles in this shear band. I may say some more words about this movie. So this movie here is just particles in a two-dimensional cell where the outer part is fixed and the inner part is moving. And that's when you construct a shear. And the shear band is attached to this wall, and this whole entire thing is the shear band. So what you do now is you measure in this region the rotation of the sticks, and then you make a histogram, and then you plot. Then there is, of course, the logarithmic scale. Many particles have zero rotation, this is the center peak. But then there are particles that rotate clockwise and other ones that rotate counterclockwise with diverse velocities. Actually, this is a very long scale. So there are some particles that rotate very, very slowly, and the other ones are very fast. And these black lines are the experimental values, and the open lines are the numerical values, which were obtained by my former PhD student, Mark Letzel, after 1 year trying to match the parameters between experiment and simulation. In one week, he had the program, and then it took him a year to make this program really reproduce the experiment with that, because it showed that there are many side effects which enter in experiments with friction with the walls and all these details which have to be taken into account at the end. Okay, let's just show you that the bearings have practical relevance, and this is also where I come from. So now let me come to the bearings themselves. First of all, as a triviality, the bearing can only work if the loops formed by the spheres or by the disks are even. Because if they, as I said, there are two types of particles, those that rotate clockwise and those that rotate counterclockwise. And since you can only connect clockwise and counterclockwise, oh my God, that is complicated. That is not on my head, it's on yours. Yeah. You want to have?
And there it is.
Yeah, sorry. Good. And so the contact network, that means the network that connects the neighboring contacting particles, is in that case a bipartite graph. That means you can split in two sets that are touching A and B, and only A touches B, like a heterosexual connection set network also. And then another simple thing is two dimensions. Two dimensions, you see, in two dimensions you have this situation, you have counterclockwise, clockwise connecting, and there is only one possible angular velocity, namely the one which is the perpendicular. Yeah? So for this reason, all contacts must have exactly the same tangential velocity. Yeah? In this case, independent of the ratio of the particles, because this is the condition for no slip, if the tangential velocities are the same. And so in two dimensions, any system of particles in which all loops are even acts as a bearing, and the only thing you can change is the angular velocity as one single parameter, so not much being said about it. But now come to three dimensions. And in three dimensions, you see loops, you have not only now angular velocities in plane, but you have a three-dimensional angular velocity vector. And so you can create these loops. And now the question is, how does this bearing behave? And what we will discover is that these three-dimensional bearings are incredibly soft. They have a lot of degrees of freedom, and it makes them very rich. And therefore, also the frustration is going to be very strongly influenced. So first, I would like to make a small calculation to talk about what are the conditions in three dimensions for a loop of particles that are rotating counterclockwise, clockwise, etc. And so I make a chain first, and then I close the chain. So the condition of a contact in a bearing is that tangential velocities at the contact must be the same. So you can translate tangential velocity in angular velocities, and then you get the condition that this expression here must be collinear with the vector connecting the centers of mass. So that you have an additional free parameter because they are collinear to each other. So you can express this R omega from one particle as the R omega from other particle minus a free constant because they are collinear to each other. So you get a free one parameter alpha at each contact. So now this is one contact. Now I put the next particle in the line. And so I can iterate this. So the J's contact follows such an expression, which for every contact I have a free parameter now, alpha. And now if I want to make now my loop, I identify the first with the last, which is my next equation. So this is now the condition for the loop because the first one is now the last one that close them. And so I have to fulfill this condition in order for having a loop being a bearing state. So this is now easy to do from this part because if I end it even, then these two things will disappear. So this already shows that you need even loops. But then next I have to also have this sum be zero. So this is the condition for my alphas. And so I can construct explicit solutions. For instance, I have here an explicit solution for my alphas being just the sum of the radii with a free constant c. So I have a free parameter now c. And if I insert this expression alpha into this sum, I can prove that this gives a zero because that's the sum of the radii. And so I have explicitly constructed for you now an entire parameter family which I can have the freedom, an extra freedom in these chains. And one can generalize this, of course. The condition that you have, I showed you, this was a vectorial condition, if we saw it again. So this here is essentially these three equations, which are so the three conditions, three bounded, let's say, that you have to fulfill. So this is like what makes up the closure. And so if you have now initially one particle, it has the three-dimensional angular velocities with the three degrees of freedom. Now at each contact you add one more, so that at the end you have 3 plus n minus 1 degrees of freedom for the chain. And when you now close it, then you have to lose another 3 degrees of freedom, so that a chain of n has n degrees of freedom extra. New as compared to two dimensions, where a chain of n has just had always 1 degree of freedom, which was the value of the angular velocity. Now we have many more degrees of freedom. And this allows us now to, we have, just for nomenclature, I should say that the solutions are we calling bearing states. So every possible way of every combination of angular velocities of such a bearing in which you have this no slip at every contact is called a bearing state. And so in three dimensions, we have a very large space of bearing states. So if I just focus on bearings in which the size of the loop is 4, which is the simplest case, then I have, as I explained before, 4 degrees of freedom for this system. And now I want to classify. The next step I would like to do it to give you a classification of all these possible bearing states. So one can do that by now defining 4 parameters for which would identify these solutions. And these parameters can be chosen, or we choose them to be these two, B and H. B is a vectorial parameter, which is like something like an overall momentum. And this is here a scalar parameter, which is something like a specific angular momentum around the center of mass. So omega angular velocity, radius, mass, and S is the positive for counterclockwise and negative for clockwise rotation. And this X here is the distance from the particular sphere from the center of mass from the bearing. So these two properties, or these 4, let's say, parameters are now classifying all my possible bearing states. And I will give you now what interpretation. So if I set H equal to 0, then the bearing state consists of all particles moving, rotating in the same direction with parallel angular velocities. So this is for the case B equals different from 0, because the B is now the direction in which the angular velocity goes, and h is 0. Now the other case, if B equals 0 and h is different from 0, then we have a hedgehog case. That means that there is in the center of the mass, the particle is not rotating, and then all the other particles are rotating around the axis that goes away from the center of mass like a star, you see? And so all the possible varying states are now combinations of either of these two cases, of the parallel one, which is the one extreme, and the hedgehog, which is another extreme. So now you have a picture of all the possible varying states that you can have for an arbitrarily big, complex system of connecting spheres in 3 dimensions. Okay, and this was the work of my student Jäger, who actually Martin Dominic. Okay, Dominic, my student Dominic, who did this classification. So if I give you now the value of B and H, I can determine for each of the spheres what is supposed to be its angular velocity, just by knowing its distance from the center of mass. So this is the advantage, and I can now show you a movie in which I start with an arbitrary random distribution of angular velocities, and then I switch in the friction between the particles, and then you will see that they will, of course, because of friction, they will slow down at the tangent, at the contact, or at the end, they will wind up in one of the possible varying states. So this is the random initial state, randomly chosen. And then I hope I have to click twice, maybe twice. Yeah, click twice. So now at this point, there's no friction. And then at some point, when they come to 1, 0, then I switch on the friction. And then now they start to slow down. And at the end, after some time, they will come to a varying state, which in this case was chosen such that this is the V equals H equals 0 case, or a parallel. And in fact, this I could have gone before, because at the beginning I can calculate V and H, and I know where it's going to go. And in fact, I always, when I have a given H and V, it's clear what is going to be the varying state. The question is just how fast I reach it. That depends on the dynamics that I use. So if I have a friction law, which is viscous, that means it's proportional to the relative velocity, then I have this decay towards the varying state. And if I have a constant friction force, I have another decay towards the, but I always, after a finite time, I reach, because the system is finite, I reach a finite time, I reach the varying state. And I can also play around, for instance, starting with one varying state, and then going to another varying state by doing a change and imposing an external load, external torque. For instance, I start with a varying state, everybody parallel, and now I just, at some point, I stop the particle in the center, and of course, then you have friction, everything slows down, and then the system converges to another varying state, which in this case must be some hedgehog state, because the center has been stopped. So this way you can play now around with these varying states. You have another one, which another movie, or a lot of movies, in which one can go through another, I can show you also. Okay. And now, of course, we can also realize this experimentally, and this is what we did here with a few spheres in contact. And you can rotate, let's say you rotate this one very slowly, and then the other one can rotate very fast. It has gears with this, of course, like gears. And you see these particles are hollow. And why they are chosen hollow is something I will tell you later, today. So you will understand this. Okay, so this is the general story about these three-dimensional bearings. And now I would like to come to the official stuff, namely the frustration of bearings. Because as I told you already, for shear bands, these bearings do not survive very long, because you see that whenever you have one of these loops which are even, whenever they start to deform and become uneven, for instance, then everything breaks down. That is bearing is frustrated. And so it's very interesting to know how this frustration actually works, because this is everywhere present. And so what I will do now, I will now study the simplest imaginable bearing, which is a square lattice, or in 3 dimensions, a cubic lattice, with even loops everywhere, yes. And I will impose now on the top in one bearing state, and on the bottom another bearing state. So for simplicity, the bearing state here is going to be that everybody's fixed. So then nobody rotates, there's no tangential velocity, zero is the same and zero everywhere. And here I take one in which I have this alternating back and forth clockwise like this. And now I would like to know what happens in between. What is the interface between two, let's say, bearing states, where this bearing state here is the typically frustrating one. When you stop one thing, then everything is frustrated. And I will use also two types of friction laws, namely viscous friction, which means that the proportion to the relative tangential velocity, the difference between the tangential velocity. And I will also look at the much more realistic Coulomb friction, which is a friction that depends on the applied pressure. And you have static friction, it's different from dynamic friction, and the static friction is higher. It is a very, let's say, non-smooth kind of function, but okay, we have to work with this because it's realistic. Yeah? And and now I will first discuss a little bit the technique. So I will use two different techniques to be sure that everything that I do is correct. One is the classical molecular dynamics or discrete element method, in which you, Coulomb instruct, and this is very popular, in which you describe this static friction and dynamic friction with these kind of functions in which you essentially do following the static friction, you attach a small spring at the contact, and then you have a certain threshold velocity, threshold value to spring stretching, which is proportional to the static friction coefficient, at which the spring is broken again. And so that way you have this kind of glue at the contact. Yeah? So this is the classic technique. And then I will also look at another technique, which gives a certain insight about the physics, namely a technique in which you systematically minimize the dissipated power. So the dissipated power P is defined like the product of velocity and velocity difference and force. You know? So and the sum over all contacts. Yeah. And now you use this technique that you systematically want to reduce this power, this dissipation. If you come to a bearing state, a real bearing state, then the dissipation is zero. So there's no contact. But since we have frustrated situation, there is always some dissipation, and you cannot avoid it. And so this is now just the formula that we use to minimize gradient minimization of the dissipated power. In one hand here for viscous contacts, and the other hand here for the one from Coulomb friction. This is a complicated derivation. I will not go into the details, but just to give you some feeling of the technical part. So we use both techniques in parallel to be sure that they give the same result. And two dimensions life is interesting, but not so difficult. You have the two options. For viscous forces, you get a continuous change between the two bearings. But something I forgotten to say, which is very important, namely that I will introduce some disorder also, because otherwise the system is boring. And so they will introduce that the friction, first of all, the viscosity in that case, the viscous constant eta, is a random number between 0.1 and 1. And in the Coulomb friction case, I will introduce that the friction coefficient mu is a random number between 0.1 and 1. So the system has some randomness at the contacts, because otherwise everything looks very, very smooth. So I will show you what happens. So if I have developed both of these configurations have the same randomness, exactly the same randomness. This is with viscous forces and this is with Coulomb forces. So you can see that this makes a huge difference. The interface between two bearings is strongly influenced now by the kind of force that you have at the contacts. Yes, and I said here the transition is smooth. It means that every contact there is some dissipated loss. With every contact you have not a single surviving bearing. Everything is destroyed somehow. But then of course the dissipation is smeared out everywhere. In the case of Coulomb friction, which you see immediately is that they form a very sharp interface. Both sides are bearing states, and between the bearing state there is this long line, which is the law of dissipation. Very much dissipation occurs on this one line, and this line can be exactly obtained as being what is called the minimal cut of this random system. It means that at every contact we have now a different friction coefficient chosen randomly, as I told you. And so the minimum cut is the line that goes from one side of the system to the other, for which the sum of all these random friction coefficients is smallest. Yes? This is the minimum, so-called minimum cut, which is something that appears in many statistical physics problems. In fact, it is very well understood. And so this can be, so the problem has been, this has been now mapped to a known issue, and so everybody is having 2 dimensions again, has been solved. The 2 dimensions is nothing special. So we go back to 3 dimensions. This is essentially why this became the physics of the letters. So in 3 dimensions, I say to myself, well, let's start thinking maybe it's like 2 dimensions. So let's start with the minimum cut. So we take I take a very small system here, 3 by 3 by 3. The reason is that only for such small systems I am able to calculate exactly the minimum cut in such a system, because I have to look at all possible cuts that exist. And so I can do it for 3 by 3 and 4 by 4, but I cannot do it for 10 by 10. It gets too heavy to calculate the minimum cut. So what I do is I start out with the minimum cut configuration, which is here one bearing and the other bearing. And then I let my machinery go, my minimization of the dissipated power or whatever by molecular dynamics calculation, and I see that I get better and better. I mean that I can reduce dissipation, and I get into states which have less dissipation, which are actually what you are finding in real life, which are much more efficient than the minimum cut. So this was a big mystery. How can it be? What is going on? And now is what I'm going to show you now. So to analyze this now in more detail, so I say this is a 10 by 10 system, a 10 by 10 by 10 system, and we also make up to 30 by 32 by 32. I mean, you see, these calculations are not trivial because it's a friction law. I mean, all I'm saying here is now I'm talking about Coulomb friction, not about viscous friction, but Coulomb friction. And so these calculations take time consuming, and therefore we cannot go to a huge system. But we can analyze, for instance, a 10 by 10 by 10 system, not looking at the minimum cut, but looking at the final state, it will evolve. And then we look at what happened. How does this system look like? And the first thing that you observe is that every single particle has at least one slip-free contact. So the gray lines correspond to contacts in which there is no slip. So you see there are many more particles which have no slip as in the other case, in 2 dimensions. Many more contacts which have no slip. And then in addition, you discover that there exist even paths. They go from one side, from one bearing to the other bearing, and along the path, at every contact, there is no slip. So the paths, they propagate torque without problem, you see. Although the entire system is frustrated, still there are these one-dimensional paths that go from one side to the other. Because the system is so soft, there's so many soft modes that we can do that. And since we have proven before that in 2 dimensions, this is not possible, because 2 dimensions have interface, there's always a jump. Every path must have a jump, yes? You can show that these 3-dimensional paths cannot go in a single plane. They have to go through different planes, because otherwise they would contradict the 2-dimensional result. And so you can actually see here, these green planes here are planes that are shown here, in which each of these planes contains a piece of this path. And the number of paths is actually very small. So we find actually 1 or 2 paths in such a box only, not more. So there are very few paths which go from one side to the other. But then essentially most contacts are slip-free. Yes, because every particle is actually connected to a network of slip-free contacts. You can reach any particle in the system through a path which is slip-free on both sides. So it's really a very soft interface. So this is what I find so fascinating, is we are all accustomed to interfaces which are sharp or more or less sharp. This is a very soft kind of interface between 2 states which are actually very clearly and very rigidly defined. Yeah? Okay, and then of course the last point according in this field is that you can also study the amount of dissipation of each contact. And in these 3-dimensional states, this is now for a 32 cube system, actually 7 ones, making histogram. What you find is that there is a very, very long distribution. We say it goes over 10 orders of magnitude in in value, in dissipated power. So they have some contacts which dissipate very, very little power, and others that contact that dissipate a lot. So this is very broad. While in 2 dimensions, essentially every contact dissipates the same amount, because in this sharp interface, or every interface has a very strong modulus in the same order. So here is a very, very broad distribution of dissipated power. So that was my story about the frustrated bearings. And now, as I told you, I will also talk about 2 other issues which are related to these bearings, which are not the frustrated, but I mean, as the first thing I would like to talk about this hollow. Remember, I talked about this hollow. I will tell you why I chosen hollow. So you can study the dynamics of this, let's say, reaching the bearing state by looking at the equations. So the equations of motion of a system of rotating particles. Here you have the moment of inertia, angular acceleration is equal to the sum of the torques. Everybody knows that. And then if I restrain myself to study viscous forces, which, as I said, we have looked at, but maybe are not so realistic in random media, then the system of equations becomes linear. And everything is linear. And then the life becomes very easy. And this is what I'm going to show you now, easy stuff. So what I want to check is now, how does this dynamics depend on the inertia or the inertia, moment of inertia of my particles? And I can modify the moment of inertia of my particles by changing here usually if you take a disk, here you have a square, or you have a R square behavior, or if you have a sphere, you have a cube behavior. But so what you can do is you can now make a generalization of the moment of inertia of a sphere by putting here a parameter alpha. Yes? So if alpha is 1, the sphere is hollow. If alpha is 2, the sphere is full, etc. Right? And alpha can be anything in between. So with this parameter alpha, I can now study the dependence of this convergence to, let's say, the dynamics on the moment of inertia of a particle. So to make a long story short, not to go into all details, I can now insert here the connectivity by the matrix of adjacency, blah, blah. And at the end of the day, I get a linear system of equations between the acceleration and the angular acceleration and the angular velocity, the acceleration and the tangential velocity, with some linear matrix which contains all information about this. And this equation has, of course, a solution in the bearing state in which all the tangential velocities are equal. So this is simple. And now what I will do is a very classical approach that it consists in looking at the perturbations of such this equation. Means what happens if I have my bearing and I now perturb in the sense that I change somewhere the velocities, yes, and how does the system then react to the bearing state? Okay, so I introduce now a perturbation. This is now, let's take bearing state, and this is now the velocity. I make a perturbation psi, and I insert this into my equation, and I just showed you, and then I again get a linear equation in the perturbation. Okay, I don't want to go into all the details. And now, if one studies the eigenvectors and eigenvalues of this perturbation, how it behaves, one can look at all the modes that you have of relaxation. So every eigenvalue corresponds to some mode. If the eigenvalue is 0, then this corresponds to a dynamic that goes from one bearing state to the other. So this is not of interest to us. So we follow now the ideas of Pecora and Carroll by looking at the difference between the fastest and the slowest relaxation time, which corresponds to the largest, the smallest, not the largest eigenvector and the smallest one, which is above 0. So there's 0 I set it out, but the next one is the first relaxation, then the largest one. The difference between the two tells you now how well you synchronize, how different. So the less different are these relaxation times, the faster you synchronize. And so what you look at is just then the ratio between the largest eigenvalue and the second eigenvalue. Okay, the second eigenvalue, if you have just one possibility to go to another bearing state, but every lambda equals 1, equals 0, eigenvalue corresponds to some trivial behavior. So anyway, look at these ratios, and then you find that this ratio here, a function of alpha, has a very strong minimum at alpha equals 1, which means concretely that what you want, the best synchronizability is for alpha equals 1, which means that the particles are hollow. So hollow particles synchronize faster than the full particles. This is the truth that I owed you before. And now I come to my last point, which is something which is very old, which actually I've told many times to Alex, everybody many times, but there's been some new stuff involved. But for the young generation, it's new. So this I will overcome now. So the question is now if you can make bearings which are spinning. It means which are not like no holes in between. Yeah? And the reason for this is that the old story that there exist tectonic plates. Between tectonic plates, there's shear band. Okay, this is on large scale shear band. And so one can imagine that also on tectonic plates, the same phenomenon that we have the shear band in the lab, as long as the particles be round. But what has been found by scientists in the 90s is that indeed between two tectonic plates, you have a kind of powder material which is called the gouge. And this powder material is very round. It's rounded, it's extremely round particles. And so the idea is maybe you have, and also it's hollow distributed in size. Interesting. So the idea is that maybe these kind of things occur also down deep in the let's say crust, but of course the density very high. So you have to be able to create these kind of bearings with high density. And so the idea is that this is you see density. If you go deeper, the density goes up, so you have to increase it. And so these are actually regions that exist along tectonic plates in which there are no earthquakes, so-called seismic gaps. And so then there can be the idea that maybe these seismic gaps are because we form these bearings. Why not? Why not going to a larger scale? And so indeed, one can imagine you have a bearing, a classical bearing. You can put into the holes, you can put other rotating discs, as long as you remember the story of rule that the loops must be even, of course. This is a crucial rule. And so you can fill up the stuff and you can reach this, you can make finally, and this is what I want to say, you can make these things, and not everything works, but you can construct them systematically, you can find solutions or to many discrete solutions, and you can find also a continuum solution. It means if you just add particles randomly and always fulfill the conditions, you can create random bearings which are space filling and which have a fractal dimension, because you have the fractal dimensions can be defined as how the pore space goes to 0 when you iterate, or it can be defined how the overall pore surface goes to infinity when you iterate. So you get this fractal dimension, which is in 2 dimensions 1.5 around, and in 3 dimensions you can do the same thing. You can also create bearings which are space filling, yes, and there I show you actually an example of the 2 different bearing states. With you remember the C that I did with my first calculation. This is for C equals 0. This is for C equals 1/2, and you see then very clearly that they rotate differently. These are all parallel kind of, and these are not. But this is now a space filling case. Yeah. And these space filling cases can be done also randomly. So you get fractal dimension of 2.6 in 3 dimensions, and this is very much in agreement with what was called by summists at that time in the real world. And so you can do this. Now this is what is more new. This stuff I told you there about was like 30 years old. And now what I say is more new, and you cannot construct this in large scale. You can make also these bearings with loops of size 6, of size 8, of size 10. And you can then, of course, take 3-dimensional bearings. Every cut that you make is a 2-dimensional bearing. Yes. So here I show you movie of when they cut through this. I go through this 3-dimensional bearing and show all the cuts that you get. And then you go through, then you see that every cut is another possible 2-dimensional space-fitting bearing. And in many of these cuts, they have fractal dimensions, but the fractal dimension is not the same. So there's a whole family of fractal dimensions that you find in these cuts. That's interesting. Just for information. And then if you look at the contact network, now this contact network, as I told you before, is bipartite, and they're just A and B. But now in the case of space-filling bearings, it's not only bipartite, it's also small world, and it's also scale-free. So it's a very interesting, rich contact network. And finally, this space-filling bearings have an interesting property also for one of the turbulence. Namely, if you now have this bearing of rotating particles and you put on some test particles, and let them be accelerated by these rotating bearings, which are, of course, as you can see, they change direction, so they go like this. So the whole motion that you get by these particles moving on a space-filling bearing disk is like super diffusive. So they grow like the displacement grows like t to the 3/2. And this is agreement with what was observed when you look at the balloon, the atmosphere. When you look at how the balloon moves in turbulent atmosphere, and this is called the Richardson law. So finally, you retrieve here a law from turbulence. And if you now go further and you calculate the energy that is stored, the rotational energy, every disk or every sphere, and look at its distribution of energies, then you find that there are quite consistent values also with Kolmogorov theory. So in that sense, this is why I used to call these space-filling bearings, I call them turbulent solids. So this was my story. Thank you very much.
Yeah.
Yeah, this is very hard for me, but I was very interested in what you said about the frustrated bearing and the state of minimum dissipation, that you had this thanks to the softness of the state, that you had the state characterizing the minimum dissipation was a state of no contact between these, in the friction, no slip contact. And the reason why I'm interested is that it resembles what we have called, when we studied chemical reactors, we found their state of minimum dissipation to be characterized by constant entropy production, that is dissipation then, through the system, if there are sufficient degrees of freedom to orient or to get to that state. And it seems that yours is a bit similar to this one that I have. I wondered.
Well, I think that this interface that we describe here in 3 dimensions is something which you can find anywhere where your system has sufficient degrees of freedom. I mean, the fact that you are
able is a very important statement to me, because degrees of freedom is not always appreciated. But boundary conditions are also very important for the result.
Yeah, but boundary conditions are fixed. In our case, I mean, we impose them. And we just, but what is interesting is that this interface is so strongly dependent on the degrees of freedom of the system.
I predicted that I would ask about this. So real ball bearings are rolling friction is not zero, and like in many systems you never have ideal motion. So if you have a small, like a tiny dissipation parameter there that's orders of magnitude smaller than the sliding friction, for instance, or the static friction, then you'd have, for your system to keep running, you have to have some external driving, even if it's small. So you break some symmetries by doing this. What happens to these frustrated bearings then?
Well, slowly, if you have dissipation at the contact, always, then you slowly come to rest. But the fact that you have to always impose some external force or torque is clear for frustrated bearings. The frustration you all the time have to impose force. And then you just, technically speaking, if you have a finite amount of, let's say, dissipation at every contact, then this distribution here will have a cutoff somewhere. That's it. It means that all other old particles will then have its finite value. That's it. But this will not. This is just a cutoff in the favor, but it's not going to change qualitatively the result. But I mean, realistically, of course, there are many problems, because also the space filling cave, and you have holes, and you have also actual gravity. So of course,
the value of that driving force, doesn't that have something to say for the solution?
The amount of driving force, yeah, just the amount of driving force is at the end equal to the dissipated.
If you have a long, if you need to make a long path, then you can have with so in frustrated three-dimensional bearings, for instance, you could end up with quite a lot of dissipation along the path. And it could be that there are other paths where you, which are not, which are that some of the in the ideal case, the nicest path becomes less good than some other not perfect path, just because it's shorter. Is that possible, or do you think that that's?
I don't think so, because it's. I mean, if you don't add everywhere, oh yeah, you're right. If you add everywhere fixed constant, then you are right. Then a shorter path would get less addition than a longer path. Yes, this could be. But I never checked.
Yeah, I think Per-Arne.
Yes.
Yeah.
Yes, Per. Yeah.
Thank you. Hi. Yes. Okay, Hans, in the beginning of your talk and towards the end of the talk, you showed real system with a lot of stationary particles. Now, you didn't really say anything about that case in the body of the talk. Can you say anything? Have you looked at the influence of stationary particles?
I mean, my particles are not always stationary in the sense that I have no translation velocities.
Yeah, no, but okay, non-rotating. You had a number of fixed, in the beginning. You had white and black and gray.
Yes.
And
yes, you're right. The reason, I mean, the beginning, what I showed you was a very frustrated system.
Yeah.
In this frustrated system, one of the bearings was the non-rotating block.
Mm-hmm.
And so this is essentially a good example for frustrated bearings. If you fix, because you see, due to Coulomb friction, there is a certain minimum amount of force you need to start let's say, a kind of slip. And so there is a big block of particles in such a granular packing that has absolutely no tangential velocity. They're completely slip-free, just because of the static friction. So these blocks that constitute a specific bearing.
Okay.
Yeah.
Thank you. You actually answered my second question, which was whether you have a condition that the static friction coefficient is larger than the dynamic friction coefficient.
Yes, I do. This is actually important fact. Yes.
Okay, thank you.
Mm-hmm. Yeah, Alex.
Yeah. Well, I found very intriguing this analogy with turbulence here. But of course, turbulence have these vortex tubes. So I was thinking, can you make the same kind of analysis for a bowl of spaghetti, that you rotate one of them? How can you put together spaghetti in such a way that you actually get things to rotate, probably on a fractal structure? I mean, if you just straight lines like this, is a two-dimensional problem.
And then you will know to have
Okay, organize spaghetti in such a way that they actually could rotate one of them and they all go accordingly.
Well, there's a problem, a mechanical problem.
Yeah.
You have a fiber which is now tortuous, and you want to now take an inner rotation just around the inner axis. Then you create constraints in this fiber, which is going to try to bend and to try to do a lot of crazy things. So this is technically, I mean, you can do it numerically, of course, no problem. But if you do it in practice, then it's not going to be stable. Kind of fibers are going to move.
But it looks like nature actually is finding a solution to this through turbulence. I mean,
I don't know if it depends on how you visualize the turbulent eddies. I mean, in two-dimensional turbulence, you don't have it anyway. You only look at, because I showed you more two-dimensional picture of that.
I mean, I think the turbulence, first of all, that's a fractal structure, right? I mean, that's where the dissipation sits on.
Yeah, the fractality is provided in this special invariant, no problem. And in two dimensions, you don't have these lines, you just have vortices which are around. I mean, there's only one possible vorticity, which is around the axis, which is perpendicular. And in three dimensions, the shape of these eddies is very complex. We have actually had work on that also, different with Suarez. And you don't have really neither circular eddies, nor you have really perfectly cylindrical ones. You have a very complex structured eddies, which are a superposition of many different wavelengths. So the picture becomes very obscure, 3 dimensions.
Yeah, I mean, you could, for example, think of a single tube like this, and the way such a vortex structure is organizing itself is to these pins.
Yeah, they all fold.
Yeah, fold like this so that you get this here to rotate.
Yeah,
and then you get a little region here where there's a little bit of frustration, but otherwise, so they make this very sharp corner.
Yeah. Yes. Okay. So it's not 3 dimensions. You cannot have the identification of the geometry. This is, you don't have circular eddies in problems. That's true. Yeah.
Yes. Thank you for that interesting talk. I have 2 questions. One, like just a small question. In the frustrated bearing part of your talk, where you go through 3D and you get these minimal paths, does the story change if you go from a square kind of lattice structure to like a cannonball packing in a way?
Cannonball packing doesn't work because the loops are not even.
Yeah, so there's no.
You only can consider that every loop must be even, otherwise it's frustrated, it doesn't work.
Yes, exactly. So we're constrained to using this rectangular grid. Yes. Okay, great. And the other thing, like you showed for the space filling spheres, you showed this distribution of fractal dimensions. What was on the x-axis there? Was that the size of the area of the cut, or the position of the cut, or?
This one was the rank. This was just the rank. So this is the largest, the second largest, third largest, etc. Just to give you a feeling of all the spread in dimensions that exist.
Yes.
And actually now, this Dominic Steger, my student, he now produced a family of 4-dimensional bearings, and then he made the cuts, and each cut is 3 dimensions. So this is why the dimensions are larger than 2, because these are now 2-dimensional cuts to 3-dimensional cuts to 4-dimensional spheres. Yeah, and so on. You can always go further.
Yeah.
It's a mathematical game. I mean, it's far away from here.
Yeah. Great, thanks.
Other questions? No, well, thank you again.
Very interesting.